All right, hi there. This is Dr. Matthew J. Trom. This is the next lecture in EML 4140 heat transfer. Let me get my laser pointer. Pew, there it is. All right. So we are still in module one talking about conduction, and this is lecture three. So we're going to talk about the heat diffusion equation and boundary conditions. The reading in the book that corresponds to this lecture is, I should say lecture three reading, so I'll fix that. Um, is chapter 2, section 3, and 2, section 4, heat diffusion equation of boundary and initial conditions. And for those of you potentially looking for a transcript that you can read, there is a permanent ADA compliant transcription, which once I record the video will be created by Zoom. And I'll drop the link right here. So if you guys are looking at the final version of the slide deck, there should be a link here that will send you to that um, ADA compliant recording with a transcript if you need it. Okay, so let's jump in. So as we're getting used to now, for those of you in fluids with me, you know this. I always try to start with a cartoon or a meme or something like that that's relevant, at least to the extent possible, to the topic. And so I was just digging around the internet for heat transfer memes, and spotted this one, which I thought was relevant since we're talking about um, kind of the fundamentals of conduction. So we have this is like the modern Marvel version of Hulk. And he's an object at high temperature and he encounters an object at low temperature. And then, of course, you have heat transfer, right, which is thermal energy transfer from hot to cold. So this is, like foundational stuff, but I thought it was funny that it's being kind of represented as a meme. And oftentimes you guys know more than I do about kind of this modern cultural stuff. So I have no idea what movie this is from or what this thing is that he is handing over to low temperature guy here. But maybe this has some deeper meaning that I'm not aware of. But so far as I can tell, it's just high temperature transferring something to low temperature, which is what heat transfer is. Okay. Um, so, where we are going in the second part of chapter two is to try to get to the heat diffusion equation, which is an equation in spatial and temporal x, y, z, and t coordinates for the temperature field. And then once you have the temperature field, um, you could basically solve for the heat flux anywhere. So I say here, the objective in conduction analysis is determining the spatial and temporal, time-based, not sure if that's the right word for that, temporal. Anyway, time-based temperature field, um, capital T's temperature of lowercase t time XYZ, so Euclidean space, um, in a medium based on the conditions imposed. So this is our goal, is to try to get this equation. Once you have that equation, then you can calculate the conductive heat flux everywhere in the material at any time using Fourier's law, right, which we've already sort of talked about. Um, Once you have the temperature equation, you can also gain a number of other important engineering insights. So, for example, if you know what the temperature field of some object looks like, you can then back calculate all of the thermal stresses, expansions, contractions that are a result of temperature, deflections that are a result of temperature. So you can basically tie the temperature field from heat transfer into mechanics of materials and kind of back out what all the deflections, expansions, and stresses are. Also very important for user safety and for electronic survivability. So this happens all the time in my capstone class where students will just be like, "Oh yeah, we'll just put all the electronics in a box to keep them safe." And then they turn the thing on and the box heats up and overheats and the electronics fry because nobody actually did the heat transfer analysis to figure out whether the box gets so hot that it burns the electronics up, or causes heat flux on the surface of the box that's so high that the user cannot touch it without getting burned. So I've had that happen too, where students will put electronic components in a metal box, and it'll be dissipating so much heat that they touch it and they'll actually burn their fingers. So obviously, in a final product that you hand to a customer, you don't want that to happen, right? That would be a lawsuit. You can use the temperature profile, the temperature equation to figure out what the temperatures on the surface of your container are and make sure that you've designed it appropriately so that it does not get too hot. And then you can also figure out what the temperature is on the inside to make sure that the electronics on the inside don't get too hot. And then, there's other places where temperature is important. So the one that's near and dear to me, of course, is thermodynamics, my favorite subject. And temperature is a state property, right? So once you know temperature and one other state property, you can find all the other properties for a particular pure substance, and then you can determine things like whether it's undergoing phase change, right? So important thermodynamic processes are driven by temperature. So and there's plenty of other examples, but those are kind of three big ones that hopefully are familiar and relevant to you guys as mechanical engineers. So so let's see if we can figure out this equation, right? Because it's super useful. So it's actually derived from first principles in your textbook. So the book introduces this kind of representative cube of material and applies the first law of thermodynamics to heat flux entering and exiting in the x direction, the y direction, the z direction. And then it gives us an internal storage term and an internal generation term. And you guys have seen this done before, right? It happened in fluids, it happened in mechanics and materials. So this type of derivation is very common in engineering to get the fundamental equations. The trick is this is a cube that has dimensions of dx, dy, dz, right? And so once you've got the equation all set up, then you take dx, dy, dz and you shrink them down to basically infinitesimal size, and everything becomes a derivative, right? And the volume cancels out and everything becomes a derivative. And then that gives you your underlying equation. So I will not go through the steps in gory detail to derive this. I don't think it's super important for undergraduates to, know where this came from or understand how to derive it. Just, you get the end equation, you know how to use it. That's the important thing. But if you do want to see how this equation is derived, please check it out in chapter 2 of the textbook. Okay, so here's the end result. So this is the full blown. It's called the heat diffusion equation, and this one is in XYZ coordinates, right? Because we started out with a cube in XYZ, right? So there is, as I'll show you later, a version in polar coordinates, cylindrical coordinates, and then also a version in spherical coordinates. But this is the Euclidean XYZ one, and so it's basically got three components. So all of these derivatives of derivatives, these represent the net thermal energy transfer, right? So that's like the conduction from one side to the other and from the bottom to the top and from the front to the back, right? That's all represented by these terms, right? And here's the conduction coefficient K, which we talked about in the last lecture quite extensively. And then there is an internal thermal energy generation term. So this is if you're sitting inside the box and you're just generating energy, thermal energy. There's a term that captures that, which is this one. So you might see that as an example if you've got some sort of like nuclear decay, right? So you've got like radiation that's being created as a result of atomic decay, could create a heat generation term. The other place where this shows up, which is a lot more common, is if you're running electricity through a wire. And the wire is generating heat, right? Dissipating the electrical energy as heat. That shows up as a generation term. So this is just basically thermal energy appearing out of nowhere, but not really out of nowhere, but out of some other type of energy that's not captured in the thermal energy equation. And then this term is the thermal energy storage term, right? So this is how much of that thermal energy is being used to heat up, or if it's being given away, to cool down um, your object, right? So you recognize CP, delta temperature over delta time from thermo, hopefully as thermal energy storage. Okay, so that's the basic equation with no assumptions built into it other than the underlying assumptions underpinning this geometry from the derivation. And so the first thing that we're going to do to simplify to what's commonly the heat diffusion equation, is we're going to say, okay, we're going to imagine that K, the thermal conductivity, is constant, not a function of temperature, which we talked about in the previous lecture as kind of the standard assumption that usually gets made for thermal conductivity, although you do know how to calculate um, situations where the K changes with temperature, because we just talked about that in lecture two. So anyway, we'll for now assume that the K is a constant value. And so if that's true, it comes out of these derivatives as a constant, right? So it pops out here, pops out here, pops out here. And then it's sitting out in front of all three of these terms. So distributive law, multiplication, I can pull it out of all the terms and then divide it through. And so then it appears here. In the denominator under the generation term, and then also it appears on the other side of the equation, right? So remember we had rho times Cp, and then we're going to divide by K, and now we have rho Cp over K, and remember, it's actually the inverse of that, K over rho Cp or K over rho C is thermal diffusivity, and so that's where this thermal diffusivity comes from on the right-hand side of the equation. So that's the underlying assumption here again is just the K is constant, right? Not a function of um, temperature and doesn't change with spatial location inside the object. And then there's an additional simplification that's typically made, which is to assume that there's no internal heat generation, right? Because that happens only in special cases, like I described, with like nuclear decay or running electric current through some sort of metal. And so that makes this term go away. The Q dot gen term goes away for no internal heat generation. And then what we're left with is the Fokker-Planck diffusion equation, right? And this is why, by the way, you guys take I was going to say linear algebra. No, no, no. Differential equations. Differential equations before you get to heat transfer, because at least in theory, you have seen all of these differential equations before. Fokker-Planck would have been solved in a differential equations class where you've got second order spatial derivative and a first order time derivative equal to each other. So you guys presumably already know how to solve these problems because you've seen them before in previous math classes. And then hopefully we'll recognize the notation. This is just what I describe kind of tongue in cheek as law of conservation of chalk. I had a chemistry teacher back 1,000 years ago when I was an undergrad who used to make the same joke, law of conservation of chalk. He just, didn't want to write out the whole equation over and over and over again. So there's shorthand for that. And, engineers and scientists do the same thing. And so this del squared operator just represents the sum of the second derivatives in the three spatial directions, right? So del squared t is just second derivative of t with respect to x, second derivative of t with respect to y, second derivative of t with respect to z added together, right? So this is that. And then this is the same thing, right? 1 over alpha times partial t over partial temperature. And then I did this two different ways. So I'm old. And so I went out on the internet and I found, just an example of what the solution to this equation looks like. And of course, it's not just one single curve. So this black curve here kind of represents the steady state at t equals infinity, right? So infinite time. And then all of these kind of family of red curves, those represent different times, right? So, or actually you can look at it the other way too, right? So depending on which direction time is going, either your object starts with the black line and you let time proceed and the peak here kind of dissipates out and widens out, or vice versa, right? It starts out kind of wide, and then the energy just gets concentrated in the center, right? So there's no, as of yet, like, no indication of which direction time is going with this plot. But as you can see, the solution to this is why you need initial conditions, by the way. The solution to this is a family of curves, right? Where there's potentially a peak in the middle, and then that peak kind of gets dissipated out over time, where, like, if I was to take the integral of this thing from negative infinity x, right? So x negative infinity, x positive infinity. The hallmark of this is that the total area under this curve is the same regardless of where you are in time, right? So you're taking some initial like concentration of energy and just letting it kind of dissipate over distance over a long period of time. Um, just out of curiosity, I asked AI, so this is ChatGPT, to come up with an equivalent slide to describe the diffusion equation. And so this is what it came up with. So I say here AI generated slide, just so you know, this is not mine. This is ChatGPT. Here's the kind of generic diffusion equation in one dimension, which I'll talk about on the next slide how we get from multiple dimensions to one dimension, but here it is in one dimension. And we have a concentration, we have a time, a position, and then we have a diffusion constant, which is sitting out there. And then just like I described before, um, depending on which direction time is going, in this case, you have an initial concentration of this could be energy, this could be particles, it's whatever. This equation shows up in multiple different places. Um, Diffusion, right, is typically the um, transfer of mass from a concentrated spot kind of spread out into a medium, right? So as represented here. So so we have an initial concentration of either energy or particles, and then as time proceeds, the particles diffuse outwards and the concentration goes down and down and down, but the total number of particles or the total amount of energy stays the same. It just spreads out over a bigger and bigger and bigger distance, right? So that's what's represented by the progression from purple to blue to green in this plot, right? So, but it looks identical to this one, right? Except it's three different times instead of almost infinitely many times. Okay, and then this is so you can actually see it happening here, right? So we have a concentration of stuff, and then time proceeds, and the concentration of stuff spreads out as time marches forward into our medium. Um, Here's a solution to the diffusion equation, right? So this is the actual concentration of stuff as a function of location and time. And it's exponential, right? And presumably you've seen this equation before in differential equations, and so you know how to solve this and how to get to this answer. We're going to end up using this solution when we get into transient conduction, transient heat transfer, but we're not there yet. So I'll sort of leave this as a primer for later. And then, as I said, the total amount of stuff is conserved, right? So whether it's particles that are diffusing in mass transfer, or whether it's energy that's diffusing in heat transfer, if you take the integral from negative infinity to infinity, you get some constant value because the total number of particles or total amount of energy doesn't change. The distribution remains Gaussian, and the width increases with time following it's the equation for standard deviation, right, which comes from a normal or Gaussian distribution. Okay, so that's the ChatGPT version of basically the same slide. So let's move forward. Okay, as kind of alluded to in the previous slide, and now done kind of more formally here, um, we can simplify this if we imagine heat transfer processes occurring in a single direction, so one-dimensional heat transfer. So I'm going to take my original diffusion equation without the generation term. I've got it here written in my law of conservation of chalk kind of terms. And I can recognize that if I've only got conduction in the x direction, that the y direction temperature gradient and the z direction temperature gradient are zero. And so I'm just left with this first term and then the heat generation term, right? So I should mention, because I've got it up here, I'm kind of ignoring it, I've got it up here. One kind of benefit for having the full-blown equation, which we'll actually use this in a couple of the example problems moving forward, is once you've got, as I mentioned, temperature of with respect to time, x, y, and z coordinates, you can plug into the Fourier equation to solve for Q, the heat flux, at any particular time, right? So that's basically what I show here, is that the heat flux as a function of time is just the spatial derivative of temperature in X, spatial derivative of temperature in Y, spatial derivative of temperature in Z. And each one of those terms, Q double prime X, Q double prime Y, Q double prime Z, are all just heat fluxes, so heat transfer per unit area in the X direction, Y direction, Z direction. You add them all up, and you get heat flux. Okay, so sorry, that was a little bit of a deviation. Okay, so we got here, right, where we've got the one-dimensional diffusion equation, right, just in the X direction. And then just like we did before in 3 dimensions, for 1 dimension, I'm going to just assume that K is a constant, so it's not related to temperature and it's not related to space. Um, I'm going to pull it out, and then I get this guy. And again, I end up with thermal diffusivity, right? So here it is actually K over rho Cp. Sitting out as the coefficient in front of the time derivative, and then I've just got the temperature derivative squared, or I should say the second derivative of temperature, um, just like I did before for the 3 dimensional version. But this is the 1 dimensional version, and at least for now, for this lecture, this is the one that we're going to end up using because, as we'll see later on in the class, um, we can have 2 or 3 spatial temperature dimensions, but the equations get really complicated because the temperatures in the different directions are kind of interacting with each other as they go. So, okay. So let's move on to another possible solution to the general thermal diffusion equation or heat diffusion equation. So this one will get us to the Poisson equation, which of course you've also seen in your differential equations classes. So we start out with the exact same equation that we had before, right? Same equation. And this time, we're going to immediately make the assumption that we are operating in steady state and that there's no thermal energy storage. So if I'm operating in steady state, this term d temperature d time goes away. And what that means is that whatever the object is that I'm interested in kind of doing the analysis on cannot store any thermal energy, right? So any thermal energy that you introduce just passes right through. I still allow the generation term to be in there. So that's a possibility that we can be just creating thermal energy basically out of nothing by converting some other form of energy that's not represented in the heat equation into thermal energy, and then that heat has to dissipate outwards. And so here's our version of the equation with the thermal energy storage gone, but the energy generation term still in there. And then I'm going to make the same assumption that I made before, that I have constant thermal conductivity. And so just like I did before, the K's all move out of the derivatives, and then I divide everything through by K, and I end up with this equation. And then law of conservation of chalk. I just write this in a compact form. So del squared T is equal to minus Q gen over K, right? So that's my Poisson equation. You guys have already seen this, right? So there's now no time derivative. It's just 3 spatial dimensions and a generation term. And again, like I said, I did this 2 different ways. I went out kind of onto the internet and found like a representative example of a solution to Poisson's equation. So here's the image that I came up with, right? So I basically got 0 temperature along the boundaries, right? Those are the boundary conditions. And then I've got a big spike in the middle, a big peak in the middle. And that peak comes from this generation term, right? So I'm basically just generating thermal energy here, and then it's conducting down and out as the temperature drops down and out to the edges of my object, right? This would be like a square plate that's hot in the middle, maintained that way by some sort of kind of external uh, heat transfer or energy generation, and then the heat's just dissipating out in all 4 directions. So just like I did before, I had the AI come up with its own version. So this is ChatGPT, so its own version of the Poisson equation slide. So here's that same equation, right, that we saw before. Here it is in Cartesian coordinates. So I've got my del squared x is equal to my minus q dot over k. T temperature, K thermal conductivity, Q is heat generation rate. And then let's see. describe steady state field. Yeah, okay, so steady state, right? I have no time dependence, but I do have some sort of source or some sort of sink for that thermal energy, right? So energy is basically getting produced and then it's getting conducted away. We're going to talk about the Laplace equation in a second. We're not there yet. Um, we still have a forcing term here. So we're going to look at like a two-dimensional plate, just like here, right? Same image as before. So I have a two-dimensional plate. I have some boundary conditions set on the exterior. I love how AI sets it to 0 Kelvin, which is of course impossible, but it does that anyway. And then I've got some kind of heat generation term in the middle, right? So probably a spot source of thermal energy generation here right at the middle. And then the heat conducts outwards in all, um, well, it's all two directions, right? In the X direction and the Y direction. So you see the hot spot in the middle and then the cold spots around the end. And so this is pretty standard. And then this is kind of like the same idea, right? I love how it says 3D solid with uniform heat generation. It's actually the exact same shape. So I've got my X direction, Y direction, and then heat in the middle, and then it dissipates outward. So these two are basically the same. I'm not sure why the AI thinks that this is two-dimensional and this is three-dimensional. It's really just the height here is representative of the temperature, not a third spatial direction. But AI. So there's a couple places where this shows up, which are listed here. So heat conduction from internal generation. We're going to talk about that or have talked about that. Electrostatics with charge density, fluid flow when you have some sort of point source, um, gravitation, diffusion. Right. So this equation, Poisson's equation, shows up in a lot of different places in physics and engineering. Okay, so let's then move on to the Laplace equation. So this is the third kind of possibility for what happens to the heat diffusion equation if conditions are such. So we have our original heat diffusion equation just like before, and now we're going to make that same assumption like we did before of constant thermal conductivity. So just like before, the thermal conductivity is not a function of location in space or temperature or time. So it comes out of the derivatives. It gets divided through just like we did before. So here's that equation. And now we're going to say in zero internal heat generation and steady state, right? So in steady state, the time dependent term goes away. And without any heat generation, this Q dot gen term goes away. And all we have is just the second derivative of temperature with respect to spatial dimensions equal to 0. And here's my law of conservation of chalk, right? So this is the compact way of writing it. Just del squared t is equal to 0. Again, you guys have already seen this in a differential equations class as Laplace's equation, and you know how to solve it, which is why we have you take differential equations before you take heat transfer. And then, like I did with the other ones, I went out onto the internet and I just looked for, representative solutions. And here's a good one, right? So we have a boundary here that's hot. Maybe it has a little hot spot in it, or maybe this whole edge is hot. And then the conditions on this edge, and that edge are all constant temperature, but colder than this edge. And so you can see the heat kind of dissipating and conducting through in those two different spatial directions. This is two-dimensional steady state. And then just like I did before, I asked AI just for fun to generate a slide on Laplace's equation. And I started looking through this and I'm like, wait, whoa, there is something wrong with this slide, which is this image is fine, right? I can definitely have a low temperature, high temperature on the boundaries, and then kind of a medium temperature on the left and right boundaries. And I get a temperature profile like this. But then look at this. This AI thing thinks that this is a reasonable answer to Laplace's equation. What's wrong with this? Well, if we look back, right, that's the solution to Poisson's equation. And the only reason that you can have a peak in temperature is because you have a generation term, right? That's basically dumping heat into your object and making it hot at that location. In Laplace's equation, there's no generation, right? There's no heat source that sits anywhere in this object. And so in steady state, you cannot have this shape. You cannot have a peak that's hot and the surroundings be cold, right? Because where does the heat come from, right? What would happen is it would immediately just dissipate away, and then you would not be in steady state anymore. So I took one look at this and I'm like, holy cow, this is wrong. And AI, in typical AI fashion, is just kind of telling me that this is the right surface contour for Laplace's equation. So mostly I put this in here just to illustrate, kind of my philosophy with respect to AI in 2026. And what I want you guys to kind of get out of this is that I am a big fan and a big proponent of using AI. I think that you absolutely should use it. In fact, if you're not using it to help you learn and to help solve problems in 2026, you're doing it wrong. So definitely use AI as a tool to guide you and help you to understand what's going on. However, you definitely need to know enough to be able to look at what the output of AI is and know if it's wrong, right? You cannot just copy and paste something that's from AI and represent it as your work without checking it to make sure that it's correct, because you can get in a lot of trouble for that. Not just, not just like ethical trouble or like trouble with your boss, but you could actually design things that are incorrect, right? That will not function as expected because AI does make mistakes. And it never knows when it makes a mistake, right? You can like, argue with it all the time. It'll kind of hold its ground for a little bit until you convince it that you're right and it's wrong. So you do have to check everything that you generate through AI to make sure that it hasn't hallucinated and given you some sort of error, some sort of erroneous answer. I also will ask that anytime you use AI, I've done this on all my AI generated slides, that you just attribute the work to AI, right? You do not claim this as your own, but you say, look, this is AI generated. So long as you're attributing work that you've kind of put through AI to the AI, and that you've checked it yourself to make sure that there aren't any glaring mistakes or any mistakes of any kind, right? This one was glaring, but you want to make sure there's no mistakes of any kind. I am perfectly fine for you to use AI in this class. In fact, like I said, you should be using it as a tool to help you learn better. But you should not just rely on it blindly without understanding what it's doing and what the underlying correct answers are. So once I spotted this, I went back into the AI and had it regenerate the slide, pointing out that there's no way that this contour could exist as a viable solution to Laplace's equation because there's no generation term. And so it corrected it, right? So this is what it came up with. Same slide, except it remade the contour for me in a way that actually makes sense, right? So you absolutely, yes, can have a cold side, a medium temperature side, and a hot side. And you can have heat transfer from the hot side to the cold side that follows this contour. That's perfectly fine for Laplace's equation. There is no heat generation here. The temperature is being maintained on the boundaries at, whatever we set those values to be, but there is no heat generation on the inside that would create like a contour, a hump, like we saw on the previous slide. So this slide I think is better, and so this is the one that I'll use. So right here's the equation that we saw before. Right here it is in the conservation of chalk version. Here it is in the Cartesian coordinate version. Steady state temperature field has no internal heat sources. Temperature at any point equals the average of the temperatures in its immediate neighborhood. That is kind of represented additionally over here. Um, Maximum principal, maximum minimum temperatures occur only on the boundary, right? Because there's no internal minimum or maximum, right? So maximum temperature here is along this boundary, minimum temperature here is along this boundary. There cannot be a temperature anywhere inside the field, inside the material that exceeds 100 Celsius or is lower than 0 Celsius. And that was immediately how I knew when I saw this that it was wrong, right? In fact, uh, yeah, it even says it right here, right? So this is the slide that has a big mistake in it. No internal maxima or minimum, right? So it actually said it correctly here, and then it drew the wrong picture. So pretty interesting. Um, anyway, contours never close around an interior point. And the field is balanced everywhere. So yeah. Okay. So where does this actually show up? We're going to use it for conduction, but it also appears in electrostatics. We've seen it in incompressible flow, right? When you remember back to fluids, this was like potential flows, right? Without any sources or sinks. The solution to that is Laplace's equation. Um, Gravitational potential and diffusion at steady state all follow Laplace's equation. So you have definitely seen this before, know how to solve it, and now it is shown up in heat transfer. Okay, so just like we did before, um, um, at least for now, we're going to just worry about this equation in a single dimension. Later on, we'll get more complicated and start solving in 2 and 3 spatial dimensions. But for chapter 2, we're going to keep everything in just one spatial dimension. And just like before, once you have the temperature field, you can run it through Fourier's equation and you can solve for the heat flux, right? We're going to show a couple of examples of that. So once I get the temperature, I can take the derivative with respect to x, with respect to y, with respect to z. Each one of those derivatives corresponds to the flux in the x, y, and z direction uh, relatively, right? And then I can add them together and I can get the total heat flux. So this will be used later um, once we get the temperature field. Okay, so for one-dimensional situations, one-dimensional heat transfer, this equation simplifies to just this, right? So I get rid of the y direction and the z direction, and I just have the x direction. I've gone back one step and let k be variable with respect to x. If it's not a variable with respect to x, it just pops out and then it gets divided through, and then I just have um, the second derivative of t with respect to x is equal to 0. Um, the important thing, though, here is again, I can solve for the temperature field and then take derivatives of my solution for the temperature field and find out information about the heat flux. One important result is that under steady state conditions with no energy generation, heat flux is constant in the direction of energy transfer, right? So, key thing, heat flux is constant in the direction of energy transfer. And how do you know that? Because if I take the second derivative of temperature with respect to x, that is, so look here, that is the first derivative of heat flux with respect to x. Um, which is 0, right? Because this is 0. So that's 0. And then if I take the integral of this, so I'm integrating in the x direction, I get a constant, right? So dqx dx equal to 0 means that or not that just q by itself in the x direction, q of x is equal to some constant. And that's just in words what's stated here. Heat flux is constant in the direction of energy transfer. So this is an important result that we're going to end up using as we solve some example problems later on, which is why I wanted to mention it here. Okay. Um, so we just did XYZ coordinates. And now we're going to do polar coordinates and spherical coordinates. And I'm going to just kind of touch on these because all the math is essentially the same. So in cylindrical coordinates, which you might know as polar coordinates, now we're, instead of dealing with a slab in XYZ, we're dealing with a cylinder. Um, so here is our cylindrical geometry, right? So the cylinder has a radius of r, its long axis is z, and then instead of like y or something like that, we have theta, which is a rotational direction. In order to get the heat diffusion equation, we do the exact same thing that we did before. We take a representative slice of this thing. This time it's dr, dz, d theta, right? So those are the 3 spatial directions. And then we just look at the heat flux through the r direction, the z direction, the theta direction, and then add up all that heat flux, preserve the potential for an energy generation term, preserve the possibility for heat storage, right, and transient temperature changes in this object. And then we just shrink the whole thing down, taking dr, dz, d theta, approaching 0, take the limit, and boop, out pops the volume goes away, and out pops this expression. So this is just the exact same heat diffusion equation as before, except it's now in polar coordinates as opposed to being in Euclidean XYZ coordinates. And the same thing is true in polar coordinates as was in XYZ coordinates, in that you can take the resulting temperature field that you get from solving this equation, plug it into Fourier's law, and out pops a heat flux. And that heat flux is now in cylindrical coordinates. So we have a R direction, a theta or a phi direction, and then a Z direction for our three different heat fluxes. Add them together and you get the total heat flux. And then if you're interested, for example, in finding the heat flux that's coming off of the cylinder, in this case, I'm just going to take my heat flux expression at R, which is the outer radius of my cylinder, and I'm going to multiply by the surface area of the cylinder, right? So 2 pi RL, R is the outer radius of the cylinder, L is the length of the cylinder. So 2 pi RL is just the total outside area of the cylinder, not the tips, not the edges, right? Top and bottom, but the circular part of the cylinder. Multiply that by my heat flux, which is in units of watts per meter squared. This is in units of meter squared. And I get the heat flux, right? Oh, there it is, heat flux. Um, so Q dot, rate of heat transfer through the entire surface area. I can also do the same thing for, well, here. Sorry, before we jump into spherical coordinates, let me just mention one key difference. Right, so in the Z direction, everything is the same in cylindrical coordinates as it is in XYZ coordinates. What changes is in the R direction, we have an R that stays here inside the derivative, and then we have another 1 over R that appears outside the derivative. Those two, if you just think about this from a units perspective, right? The units of this thing have to be temperature per distance squared. Um, so this R in the numerator and this R in the denominator cancel each other out in terms of units to get us to the correct units, T per distance squared. But one of these lives inside this derivative and the other one lives outside of this derivative. And so if you have an expression for T, that T does get multiplied by this R before you take this derivative and then divide by this R, right? So that's an important difference that did not exist in XYZ space, right? There was no like weird, let's look at this one. No weird like X sitting in here and then 1 over X sitting in here. And so that does actually create some interesting phenomena, which we'll talk about later when we get into conduction in multiple dimensions. That doesn't exist in XYZ, but does exist in polar coordinates. And then, of course, the same thing is true to some extent in the rotational direction, right? Because the units have to be temperature per distance squared. But I'm taking a derivative with respect to phi or with respect to theta, right? So that's my rotational direction. The rotational direction has no distance associated with it. So this derivative by itself just has units of temperature. This derivative has units of temperature. In order to get the correct units, temperature per distance squared, I've got to have the distance squared sitting out front here. This one is not inside the derivatives, and so you end up just taking your uh, temperature equation, taking the derivative with respect to phi or theta once, taking it twice, and then dividing by r squared. So the effect that I was talking about before, that's very weird in the r direction by having this r sitting inside the derivative, does not appear in this term. But you do have to divide by r squared at the end to get the units to come out right. So that can have some strange consequences that are slightly different than the Euclidean solution. But we'll dig much deeper into that later on. I just wanted to point it out here because you could kind of see it in its purest form, and we'll get back to this later, but this is kind of your first introduction to it. In spherical coordinates, same idea as before, right? So now we're just taking a chunk of the sphere. We have the radial direction, we have a theta direction, we have a phi direction. So two rotational directions instead of one rotational direction because it's a sphere. And then we have our kind of representative volume, dr, d theta, d phi. And then we look at the temperature entering and leaving on each of these faces relative to face in the previous or the same direction. And then we allow for a generation term and we allow for a temperature with respect to time, energy storage term, right? Time derivative term. And then same game as before, we take this and we just shrink it down by driving dx, d theta, d phi all the way down to zero. The volumes drop away, and you end up with this expression for spherical coordinates for the heat diffusion equation. And the same game as before, right? So we take the derivative in the r direction, derivative in the theta direction, derivative in the phi direction. These are kind of specially modified because we're in spherical coordinates. And so we've got to take 1 over r here and then 1 over r sine theta here to get the units to work out correctly. But ultimately, these are just an r, theta, and phi component of the total heat flux. We add them together and then we get the heat flux, so heat per unit area. And then if you wanted to get the total heat transfer rate out of the surface of the sphere, you would just take the heat flux at r, which is the edge of the sphere, right, the radius of the sphere, and multiply that by the area, right, so the surface area of the sphere, 4 pi r squared, and that gives you now the total heat transfer total heat transfer rate out of the surface of the sphere, right? So same as with cylindrical, same as with Euclidean. The only thing that really changes here is because we're in spherical coordinates, we have to deal with kind of these extra terms in the denominators of the derivatives, which are there mostly to help the units work out. So that same kind of weirdness that I described here for this term in cylindrical coordinates also appears in cylindrical coordinates, yeah, appears here in spherical coordinates. But in this case, I have an r squared living in front of the derivative, right? So I'm going to take this term, put in my t value, take this derivative, multiply by r squared, and then take the derivative of that with respect to r, and then divide by r squared. The units work out fine, but this term sitting here inside the derivative does sometimes create some weirdness, right? So just be aware that that's there. And then because my other two derivatives are uh, angles, right? So rotational directions. I have to divide by r squared over sine squared theta to get the units here to work out, and then same thing is true here. And then notice that there is this sine theta that's sitting inside the derivative here, and so I have to multiply my dt d theta solution by that sine theta, and then take the derivative, and then divide by r squared sine theta to get the right result, right? So you can get some kind of weird effects in spherical coordinates that don't show up in Euclidean coordinates because of these terms that end up being embedded inside the derivative. So just be aware of that. We'll tackle this again when we get to cylindrical and polar coordinates, cylindrical and spherical coordinates later on in chapter 3. But I just want to point it out here because we've got the equations kind of in their freshly derived purest form just sitting right in front of us. Okay. So the other thing that we want to talk about in this lecture is boundary conditions and initial conditions. So if you remember from your differential equations class, anytime you have a differential equation, you have to have boundary conditions, right? Differential equations and boundary conditions go hand in hand. A differential equation without boundary conditions is an incomplete differential equation. And in our case, we're going to have some spatial boundary conditions and we're going to have some temporal, some time boundary conditions. And you have to have as many boundary conditions in space and time as you have orders in your differential equation, right? So I say here, differential equations have two parts: the solution, which we've now just covered in great detail, and the boundary and initial conditions. The order of the equations imparts the number of needed boundary or initial conditions to solve the differential equation. So for the heat diffusion equation, let's just go back just so that we can take a look at it. And it's right. So like this guy, right? We have, it's actually maybe easier to see it here. We have two spatial orders, right? So second derivative with respect to x, y, and z. So that's spatial order of 2. And we have a time order, temporal order of 1, derivative of temperature with respect to time. So we need, let's go back. Here we are. We need one, for the heat diffusion equation in its complete form, one time initial condition and two space initial conditions. in order to get a solution for the full heat diffusion equation that has both time and spatial location. For Poisson's equation and also Laplace's equation, in both of those cases, remember the time derivative goes away. There's no change in time, change in temperature with respect to time, no thermal energy storage. And so the requirement for initial conditions with respect to time go away. And we just have the requirement for two spatial conditions, right? So two spatial for Poisson, two spatial for Laplace. So make sure as you're going through and solving your differential equations, right, or writing out your equations that you know what the boundary conditions are, because if you do not, you cannot solve those equations, right? So a lot of times people will get hung up on this. Um, okay, there are four different main heat transfer boundary conditions. There's certainly more than four, but there's four main ones that we'll encounter in this class, right? So as you're setting up your equations and looking to solve them, you want to be able to identify which of these four main types of boundary conditions are the ones that are represented in your problem. So the first one is constant surface temperature, right? So you have some temperature at some location that's set in space. And so, like, for example, the temperature at location x equals 0 and all time is some set value, Ts. So that could be your first boundary condition. We actually encountered this, if we go back, right? We encountered this here with Laplace's equation, right? So we set a boundary here of 100 Celsius. We set a boundary here of 0 Celsius, a boundary here of 50 Celsius. And so these gave us our initial conditions that allowed us to solve for what the temperature was internally inside this two-dimensional plate, which is governed by Laplace's equation, right? So that's an example of a spatial boundary condition. We can also have a boundary condition of constant heat flux, right? So the Q is constant at a surface. And so what that gives you is the slope of the temperature field at that spot is equal to some constant value. Um, so this gives you um, the first derivative of temperature at that spot, which you can use as a boundary condition as you're solving, as you're integrating your way through the heat diffusion equation. So a place where this shows up, and we'll actually see this in one of the examples, is if you have something that's axisymmetric, right? So something that's axisymmetric will have no heat flux at the center, right? So the derivative of temperature with respect to some sort of spatial direction is constant at that spot, right? And the heat flux there is 0. Um, so that's constant heat flux. Um, the third possibility is a convective boundary condition. So in convection, you've got conduction that's moving heat out of your solid material and then into your fluid, which is blowing past at some ambient temperature and some given, usually forced heat transfer convection coefficient. And so the temperature at that particular spot at all time is basically set by equating the conduction out into the convection into this gas that's blowing past the object. And so that's represented mathematically here, right? So we have, here's the conduction through Fourier's law, which is leaving, and then here's the convection, which is absorbing that same thermal energy. They're equal to each other. And so you can also use this as a boundary condition. And then the final possibility that's sort of a major one that we run into is that you have an insulated surface. So at an insulated surface, heat cannot transfer through, and therefore there cannot be a temperature gradient beyond that surface. So the temperature gradient just flattens out, and you end up with, for example, dt dx at that spot is equal to 0. So that's the third one, or the fourth one. So always keep in mind as you're kind of marching through your problems, what your boundary conditions are, and try to identify them as one of these four main boundary conditions that we encounter in the heat transfer class. Okay, so that's it for the technical content for this lecture. Let's move on to solve a couple of example problems. Okay, here's example 1. So we have a plane wall of thickness 2L that tripped me up in the beginning. So 2L, um, 0 is in the middle of the wall, and then it's 50 millimeters to the right, 50 millimeters to the left, gives us a 2L wall thickness of 100 millimeters. So that's the thickness with a uniform heat generation of 1,000 watts per cubic meter. So here's that heat generation that's just kind of happening. We're not told how it happens, but there it is. And surface temperature of 303.15 Kelvin, with an internal temperature distribution of T as a function of X is equal to 10 Kelvin per meter squared times L squared minus X squared. L, by the way, is the same L, right? And then X is a variable. Um, so the temperature distribution looks like this. It's high in the middle. And then as X increases away from 0, both in the positive and the negative direction, temperature goes down, plus 303.15 Kelvin. And notice in all of these, right, the figure is in degrees Celsius. We do not do degrees Celsius in heat transfer. So I have just converted everything to Kelvin so that you don't have to. But that's where all these weird 303.15s come from. Those are all these 20 and 30 degrees all converted up. Okay, the wall is surrounded by ambient air at 293.15 Kelvin, 20 degrees Celsius. Find the thermal conductivity of the wall in watts per meter Kelvin and the convective heat transfer coefficient in the gas in watts per meter squared Kelvin. Okay, so that's the problem setup. Okay, so first we're going to make some engineering assumptions. So we're going to assume the system is in steady state. And we're also going to assume that the thermal conductivity is constant and independent of temperature. And so with those two assumptions, right, so I'm going to go back to the heat diffusion equation, right, which is the most general version of the conduction equation, and I'm going to apply these assumptions. Constant thermal conductivity allows me to pull these K values out of the derivatives, and they sit out in front of the derivatives because they're constant. And then assuming the system is in steady state allows me to eliminate the time derivative term, the energy accumulation term, so there's no energy accumulation in the system. And then we're also going to recognize that this is a one-dimensional problem. So it's right, just one-dimensional conduction in the X direction. There's no heat transfer in the Y direction, up and down. There's no heat direct transfer into the screen. So one-dimensional heat transfer in the X direction through the plane wall, with, of course, internal generation, right? So I'm going to leave this term alone because we're told that there's some internal generation, so that term has to stay. So what we end up with is Poisson's equation. Right, and so here's how it's derived. So we end up with second derivative of temperature with respect to X is equal to minus Q gen over K. Q gen is this heat generation term, and then K, of course, is the thermal conductivity coefficient that came out of the derivative and then got divided through. This negative sign just comes from the fact that I'm moving this guy to the other side of the equation to make this look like Poisson's equation in one spatial direction. Okay, so that's where the equation comes from. All right, so step number 3. Is what we're given the temperature distribution, right? It's given to us. I read it off before, but here it is again. So temperature in the X direction is constant 10 kelvins per meter squared times L squared minus X squared plus 303.15 Kelvin. And so we're just going to start plugging that into the Poisson's equation that we got from part 2 to see what comes out. And what you will find is that the only thing that you don't know in the resulting equation is the thermal conductivity. So we end up solving for that. So here I am taking the first derivative, right? So this term stays, this guy's a constant, so it goes away. The negative sign comes through, this exponent comes down to multiply this by 2. So this minus 2 is this minus sign and this exponent as I take the derivative. And then what I'm left with is just x all by itself. This term is a constant, so that goes away. So that's my derivative with respect to x. Now I want to take a second derivative with respect to x. And so all I'm doing there is, right, this is just like constant times x. And so I just am left with that constant. And the oh, Q gen is given, right? So this is given as 1,000 watts per meter cubed. And of course I don't know K, but that's what I'm looking for, right? So I can now take the pieces that I have, right? So the second derivative of temperature with respect to x and Q gen, and right, like here's the equation. So I'm just plugging in my second derivative of temperature that I now have like a value for, and I'm plugging in my Q gen, which I have a value for, and just solving for K. So here I am solving for K, plugging in the derivative, plugging in 1,000 watts per meter cubed, solving for K, and I get 50 watts per meter squared Kelvin, and that gets a green check because this is the same answer that is in the book. This is a textbook problem, by the way. So I'm just copying out of the textbook the problem statement and solving it, and I get the same answer the book does. So that's that one. The second thing that we have to do, let's see here, was, oh, find the convective heat transfer coefficient, right? So we just found the thermal conductivity, and now we have to find convective heat transfer. Okay, so I'm going to solve that by recognizing that at the boundary, so let's go back, right? At this boundary, it's actually even shown on this figure. On this boundary, I've got conduction going out, or I should say conduction going into this control volume, and then I've got conduction, no, this is convection going out, right? So conduction in, convection out, and because we're in steady state, there's no energy storage, and so those two have to be equal to each other. And so this is the convective boundary condition, which, just as a quick reminder, is one of our four main types of heat transfer boundary conditions. So here it is. And all this is doing is just saying that, hey, the conduction at this interface between the solid and the vapor, solid and the solid and the fluid, there we go, solid and the fluid, is equal to the heat that gets conducted into the fluid, right? So I'm going to just use um, that boundary condition. Which is true. Let's see, boundary condition x equals 0 and x equals L. Actually, this should say x equals, see, I told you I got messed up. This should say x equals minus L, right? Because, right, minus L is here and plus L is here. So I'll change that when we post the slides. But um, okay, it doesn't change the outcome. So what this should say is that the minus k dt dx at x equals L, or minus L, they're the same, is equal to h of t infinity minus t of, this should say L or minus L times, or also a function of t, right? So little mix up there with the notation, but basically what I'm saying is just the conduction is equal to the convection at the boundary where x equals L. Okay, so you always then run into this question of which one of these is hotter, and remembering that we want to, at least the way that I do it, is I determine to the extent that I can which one is hotter, and then I put that one first, so that when I'm subtracting, I always end up with a positive value here. And then I figure out when I'm doing my energy balance, whether it's a Q in or a Q out, and that then determines whether there's a negative sign sitting in front of it or not. But I always switch the order of these as I need to make sure that the convective term, at least in the way that I solve this equation, is positive. So here I am doing that, right? Recognizing that it's actually going to be the slab that's hotter, right? So this is going to be hotter than this. You can actually see me doing it down here, right? I switch these two so that the hotter slab um, gives me um, a positive value for convection. So we'll come back to that. Okay, so I know. Oh, see here I actually wrote it right. X equals L, right? So here, and here I wrote it right too. T of L. Ha, look at that. So I know this value dt dx because I did the derivative of my internal temperature profile before. So it's minus 2 times 10 kelvins per meter squared times X. But we're going to solve this at X equals L. So here I am plugging in. Um, let's see. I'm trying to figure out what I did here. Oh. Okay, right. So this is the equation itself, right? So let's go back. This is this equation, right? So this is my temperature profile, and I've got L squared minus X squared, but I'm solving this guy at X equals L. So here's that coefficient that's sitting out in front. Here's L squared. Here's X squared. But hey, look, they're the same thing, right? So these two guys cancel. This whole term is zero, and I'm just left with 303.15 Kelvin. So that's the temperature of the slab right at the edge of the slab is 303.15 Kelvin. Okay, so now I've got that temperature, and I can then plug that value in for this T of L in my convection side of the equation. And I already know everything from the conduction side, right? I solved K in the previous part. So here's that 50 watts per meter Kelvin from the previous part. Here's dt dx, so minus 2 times 10 Kelvin per meter squared times, that's my X value at L, 0.05 meters. And this equals my convection coefficient, which is what I'm actually trying to solve for, multiplied by, this is TL and this is T infinity, right? And again, I switch them because in the way that I do it, I always want my convection coefficient to be, or my convective heat transfer to be positive. And then when I do the energy balance, I sort out whether it's a Q in or a Q out, and then assign the negative sign appropriately, right? So in this case, it's a Q. Let's see. Uh, yeah, okay. So here it is, right? It's equal to whatever is entering, right? And so what I have entering, let's go back again. What I have entering is the conductive heat transfer, and what I have leaving is the convective heat transfer. So they should be equal and opposite to each other on opposite sides of the equal sign, right? Which is yeah, that works out, right? Because this negative and this negative cancel each other out. So this guy's positive, and then I've switched these two so that this guy's positive. Yes, okay, so that's right. They have the same sign. Okay, so now I'm just solving for H, right? So I just move all this to the other side by division. There it is. I'm dividing, and lo and behold, I get 5 watts per meter squared Kelvin, and that agrees with the book, the solutions of the book. So green check mark. Now notice, right? So this is a little bit hand wavy, right? This, do you switch these temperatures, yes or no? If I did not switch the temperatures, what would end up happening is I would end up with a negative convection coefficient, right? I get negative 5 watts per meter squared Kelvin, and that would tell me that I'd done something wrong, right, with these temperatures. I would have essentially, if you're looking back here, that's the equivalent of saying that this convective heat transfer coefficient is going into the slab, right? I'm transferring heat this way, as opposed to transferring heat out, which is the correct way. So I'd end up with a negative convection coefficient, and that's how I know that I need to switch these two to get this guy to be positive, so that when this negative sign and that negative sign cancel each other out, I get a positive convection coefficient. Okay. All right, so we got that one figured out. Let's do the next one. Okay, so example 2. We have air, and it's heated in a hair dryer, so something hopefully most of you are familiar with, by blowing it across a coiled wire, usually nichrome wire, through which an electric current is passed. Thermal energy is generated by electric resistance heating within the wire, and is transferred by convection from the wire surface to the air. Consider conditions for which the wire is initially at room temperature, Ti, and resistance heating is concurrently initiated with the airflow at T equals 0, right? So basically we're turning on the hair dryer, right? And what that means is the air starts flowing, but also we're running electric current through this wire at time equals zero. Okay, the length and radius of the wire are 5 meters and 1 millimeter respectively. So 0.5 meters long and 1 millimeter. It's actually 2 millimeters in diameter, 1 millimeter in radius. And then we're asked to do a couple things. So we want to plot the temperature at any R value and at T equals zero, the temperature at any R value and T equals infinity, and then a representative curve or curves for T temperature as a function of both R and T, kind of between these two extremes, right? Between time equals zero and time equals infinity. So plot for temperature, and then we want a plot for heat flux at R equals zero. Okay. So just like before, R equals zero is the center of the wire, right? So here's the wire. It's all coiled up. Here's the air blowing over it. But then we've got kind of a zoomed in version of it here so we can see what's going on at the smaller scale. And R equals zero is at the center of the wire, and R naught is the edge of the wire, right? So if I go back here, yeah, R equals zero is the center of the wire, and then for for any time, and then we want the heat flux for R naught at any time. So R naught again is the edge, and then heat flux for R naught and T equals infinity. So once this thing reaches steady state temperature, what's the temperature on the edge of the wire? Okay. Then they want to know what is the volumetric rate of thermal energy generation for the wire for a power absorption of 500 watts. So that's a kind of a really weird way of putting it. Um, by power absorption, they just mean you're running 500 watts of power through the wire, right? So they want to know what the volumetric rate of thermal energy generation is. How much energy per unit volume are you generating for 500 watts of input power? And then part D is what is Q dot double prime? So heat flux per unit area at the wall and T infinity. Okay. So I get it. So we plotted it before, right? But now they actually want the actual value, the numerical value. Um, the convection heat flux under steady state conditions. Yeah, that's what that term is. Okay, so let's tackle these one at a time. So we need to, like we did before, make some engineering assumptions. So we're going to assume that thermal conductivity K is constant and independent of temperature. That, as we've done before, allows us to pull that temperature out of the derivatives and the heat diffusion equation. We're also going to assume uniform resistive heating, right? So there's no impurities in this copper wire that would cause it to get hotter at one spot and not as hot in some other spot when we run current through it. So it's going to have the same volumetric heat generation all the way through. So those are my two assumptions. All right, we're going to recognize this problem as a one-dimensional conduction problem in cylindrical coordinates, right? Not Euclidean XYZ coordinates, but cylindrical coordinates, right? And we've talked about cylindrical coordinates in the lecture, and things can get a little weird with the radial derivative because that R, where is it? There it is. That R lives inside the derivative, right? Inside this DDR. So we have to be cognizant of that. That's a possibility. Possibility there of generating some unusual or unexpected features in my temperature profile. So just be aware of that. Got to be careful of it. Okay, so it's still one-dimensional conduction, and it's the heat diffusion equation with generation, and it's still in one dimension, right? Because so if we look back, right, we're talking about the heat transfer in the radial direction. There's no heat transfer up and down the coil, and then there's no heat transfer kind of azimuthally in the theta direction or the phi direction around the axis of the coil. It's just heat transfer from the center outwards, right? So that's still one-dimensional heat transfer, although it's in cylindrical coordinates. So we are going to solve this thing using our polar coordinate version of the heat diffusion equation, and we're immediately going to eliminate the phi term and the z term because, as I just said, there's no heat transfer in either of those two directions, no temperature gradient in either of those two directions. So these spatial derivatives in those two directions go to zero, which makes those terms zero. I'm going to preserve the heat generation term because I have electricity running through the wire, and that electrical energy is going to get turned into thermal energy, which I need to account for. And then, at least for now, I'm going to preserve the time derivative term because we're talking about like t equals zero, t equals infinity, values of t in the middle, right? So there may very well be some energy storage and some need to calculate a temperature with respect to time. So I'm going to leave this there. With my assumption that k is constant, I'm going to pull k out of all my derivatives. The only derivative that's left is this one, so I'm going to k out of this derivative. And here I am just rewriting that same expression. So I'm rewriting this guy, but with k pulls out as a constant, divided through both sides, and then this q generation term moved to the other side of the equation. So here's the negative sign for that. And then remember, k over rho Cp is alpha, and so alpha ends up in the denominator in front of the time dependence term. And again, this is a problem pulled out of the textbook. So green check, this is the correct equation. Okay, so step number 4. Oh, I think we skipped step 3. Okay, so this should be step 3. Let's see, what are we doing? Okay, we're plotting T, and we're plotting Q. Okay, so yeah, here it is. Here it is. So we're plotting. Okay, so we got to figure out how to plot temperature as a function of r, the radius for the initial time, temperature across the radius at the final time, which is just out at infinity when the whole thing has reached steady state, and then some representative curves. Okay, so and here they are. So let's see how we did this. So the initial condition, temperature um, at any radial location at t equals 0. Oh, this was given, right? Yeah, yeah, right. It's right here. Consider conditions for which the wire is initially at room temperature. Okay, so all this says is that the entire wire, right, for all values of R at t equals 0 is just Ti, the initial temperature, room temperature. Okay, so that's the initial condition. And then because this is a differential equation, right, differential equation, we've got to come up with spatial boundary conditions. So and temporal boundary conditions. So this is my temporal boundary condition. This is my I need 2 spatial boundary conditions. So the first one is that dTdr at r equals 0 is 0. Okay, and I specifically put this chart here, this figure here, to remind myself to explain this. We talked about it a little bit when we were going through the lecture, but let's, just kind of think through. And in fact, I'm going to cheat here a little bit. I'm going to go back to the previous problem. And I recognize that this is not a cylindrical, right? Not a cylinder, not cylindrical coordinates, but this gives you a sense of what that temperature profile potentially looks like, because this is a similar problem that's just, XYZ coordinates instead of polar coordinates. But look what happens right here, right? Right at the center of the slab, the first derivative of that temperature is 0. Because it's symmetrical from 0 to positive x and 0 to negative x. So the same is true, even though we don't have a temperature profile drawn yet. The same thing is true here, right? This is a center line, and it's the geometry is axisymmetric, and so the temperature at r equals 0 at that center line, the derivative of temperature must be 0, right? And that makes sense too from a conduction standpoint, right? Because you don't have any conduction in the r direction right at the middle, right? Heat is definitely moving from r equals 0 outwards, but it's not moving inwards, right? Because it's the center of the wire, right? So the first derivative of temperature must be 0 here to ensure that there's no conduction like into the center of the wire, because that just physically wouldn't make any sense. Okay, so we've got that boundary condition, and then the second spatial boundary condition is that at r equals r naught, we've got the convective boundary, right? So out here, where r equals r naught at the outside radius of the wire, we know that we've got convective heat transfer, that's this, convective heat transfer that's pulling heat away at the same rate that it's getting generated and conducted and dissipated. Okay, so we've got this equation, and then I've just got my little reminder to myself, which is hotter. And in this case, the wire is going to heat up and be hotter than the ambient environment. So this temperature, which is the temperature of the outside surface of the wire at any time, is going to be hotter than T infinity. And so this term leads and this term follows. And so you end up with a positive value here. Okay, so now we're going to plot these, and I will admit that I did steal this from the book. Um, I suppose I could have plotted it myself by hand, but it would have been very messy. So let's just interpret this. So the temperature at any R value at T equals 0 is just the initial temperature, right? So here's the initial temperature, and that temperature is uniform all the way through from the R equals 0 center line to R equals R naught, um, the edge of the wire. Okay, so we got that one. And then let's do the other extreme, which is T at any R for infinite time. Okay, so now we've basically reached steady state, right? So the inside of the wire, remember this wire has electric current running through it, so it's hot. The inside of the wire is the hottest spot. And then notice again, right, the derivative here, temperature with respect to R is 0, right? So it's going to flatten out here. The temperature profile is going to flatten out here. And then it's going to fall off as we go towards the edge. And when we get to the edge, we've got some constant value of the slope, right? dTdr is some constant value. So you can see that here in the convective boundary coefficient, or sorry, the convective boundary condition, that's the word I'm looking for, right? So this guy, because the air is colder than the copper wire, is sloping downwards, but that slope is constant. Once that spot hits the edge of the wire, okay, so we've got that shape, which makes sense, and then we have to look for a couple of representative curves for temperature as a function of R and T for values of T that are between 0 and infinity, right? So you could, I think, imagine what happens here as the wire heats up. These curves just kind of increase in height, they increase in curviness, and this flat line essentially over time evolves into this curved line as time progresses forward. So that's that plot. Okay, we're also asked to plot the heat flux at R equals 0 at any time, at R equals R naught at any time. So R naught, remember, is the outside wall, the outside of the wire. And then the heat flux at the outside of the wire at T equals infinity. Okay, so a couple of curves there. In order to get these heat fluxes, remember we've got this trick that I showed you from let's go way back into the lecture just to show you where it was there. Yeah, it's here, right? So I can calculate the heat flux in cylindrical coordinates or spherical coordinates or whatever I happen to be in by taking just the derivatives of my temperature profile using Fourier's law and just adding them together, right? In this case, this term is 0 and that term is 0 because I don't have heat transfer in the azimuth or the z directions. And so I'm just going to end up with the heat flux is equal to minus k dt dr. Where is it? Yeah, there it is. Right, so here's that same equation, and I've only got one direction, so I've got my Q double prime, so my heat flux in the R direction for any value of R and T is just this first term because the other two terms are 0 because there's no heat transfer in those directions. Okay, so this is what I'm using to essentially come up with the plot for these three conditions. Okay, and then we're also going to recall, just some spatial boundary conditions from before. The fact that this should say R, dt dr at R equals 0 is 0, right? That's that symmetrical initial boundary condition that I was talking about. And we also have a convective condition at R equals R naught. Okay, so how do we get these plots? So let's start out with this one. So Q double prime at R equals 0 and NET. So that's this. Let me think through. Oh, yeah, right. Okay, right. So Q at R equals 0 is that's just the center, right? So that's the center of the wire, which we've already said. The Q has to be 0 there because of the axisymmetric condition, because of this one. Right. Okay. So this is just going to be a flat line that corresponds to Q equals 0 the whole time. Okay. So that one makes sense. Okay. The second plot is Q of R naught at T. Q of R naught at T. Okay. So this is the warm up, right? So the wire is gonna heat up. This is the outside surface of the wire. So the outside surface of the wire is heating up as time progresses forward. And so we have this kind of upwards curve that's sloping towards an asymptotic value. What's the asymptotic value? Well, the asymptotic value is when t time is equal to infinity. And when time is equal to infinity, it's just a constant value, right? So, in other words, the wire has reached, let's go back. It's reached steady state here, right? And so this value, the temperature at the wall is now a constant fixed value. And so the heat flux off of the wall is going to be a constant fixed value. And then this curve, which is growing, basically is growing towards that asymptotic value at t equals time equals infinity. Okay. Okay. So we've got three plots, all seem to make sense given what we know about this wire and what it's doing. So then let's move on to part C, which is, okay, we're asked to find the volumetric heat generation in the wire based on the given information. So, okay, we're told that the wire has 500 watts running through it, and we just want the volumetric heat generation. And so it's just 500 watts divided by the total volume of the wire. The volume of the wire is just, it's a cylinder, right? So this is the length of the wire. This is the radius of the wire. And then pi over 4 gets me from a radius to a cross-sectional area. If I square it, multiply by pi over 4. So cross-sectional area times length, that's volume. Take that as the denominator over or under 500, and I get 3.18 times 10 to the 8th watts per cubic meter. So that's my volumetric heat flux or volumetric heat generation. This, again, is borrowed from the textbook, and so that's same as the value of the book, so I get a green check there. And then the last part is find the convection heat flux under steady state conditions. Okay, under steady state conditions. Okay. So we already talked about this, at least qualitatively, but we didn't calculate the value, right? So if you let time go long enough, right? So the heat flux at the wall at time equals infinity, you're going to reach a constant temperature at the wall. And because you have a constant temperature at the wall, the convective heat transfer from the wall out into the gas is also going to be a constant, fixed, unchanging heat flux value, right? So that's this dotted line here, this asymptotic value up at the top, right? So all we're doing now is just calculating what the numerical value is representing this spot on the temperature versus radius chart, and this line on the heat flux versus time chart. Okay, so we know that we've got, okay, this is not bad at all. We know that we've got the uh, um, 500 watts is getting, hang on. I need to think. Oh, yeah. Okay. This is a sorry, I'm having a like how many primes are there? This one is per unit volume, this one is per unit area. So I'm taking my 500 watts and I'm just dividing it by the area of the outside of the wire, right? Okay. And the wire, of course, is just a big long coiled cylinder. So here's my 500 watts. It gets divided by 2 pi um, R naught, right? So 2 pi R is the um, circumference of the circle that makes up, if we go back, right? this thing is a circle, and that's just the circumference of the circle, and then I'm just multiplying it by L, which is the total length of the wire, right? The whole length of the wire is L. Okay, so that's where I get this from, right? So here's 2 pi r naught times L. Here I am putting in the values, and I get 1.59 times 10 to the fifth watts per cubic meter. And that agrees with what is in the textbook. So I get a green check for that one. Okay, cool. One more example, and then we'll wrap it up. Okay, so in this example, I have a plain wall, and I'm given some properties for the wall. So it has a density of 7,000 kilograms per cubic meter, a specific heat, a constant pressure. We'll see in a second that doesn't matter, right? Because this is a solid, but okay, fine. So Cp is equal to 450 joules per kilogram Kelvin. This is just going to become C because Cp and Cv are the same value for solids. If you remember that from thermo. And then I have a thermal conductivity of 90 watts per meter Kelvin. So this plane wall has all those properties. It has a thickness of L is equal to 0.1 meters, right? So I'm starting from X equals 0 on the far left, and then I'm marching 0.1 meters here to L, and that distance is given here. Okay, so experiences uniform volumetric heating. Ah, my friend, uniform volumetric heating at a rate of Q dot triple prime. One surface of the wall, which is the X equals 0 surface, is insulated. And so, haha, we know something about insulated surfaces, right? That's one of our boundary conditions from before, right? Insulated surface. So just keep that in mind. That's probably going to come up in this problem. Boundary condition at the wall is that dt dx is equal to 0. Okay, so we're given that piece of information. And then let's see what else. Okay, other surface is exposed to fluid at T infinity equals 293.15 Kelvin, with a convective heat transfer characterized by H is equal to 1,000 watts per meter squared Kelvin, right? So we have a convective boundary here. Initially, the temperature distribution on the wall, ooh, this is interesting. Temperature distribution in the wall, T as a function of X and T, lowercase t, for time less than 0, right? So this is basically before the problem starts, is given as 573.15 Kelvin minus 1 times 10 to the fourth Kelvin per meter squared, all multiplied by x squared. And we're told that x is in meters. Okay, and then suddenly the volumetric heat generation is deactivated, right? So it gets shut off at time equals 0. So Q dot, which is that generation term, goes away as the problem starts. But of course, it was there before. And so this wall had some weird temperature profile in it, which is given by this equation. And I bet you that temperature profile now is going to like settle down to a constant temperature. And we're going to be asked various things about, what's the temperature at this spot at this particular time, or how much heat flux was pulled out of this thing, to get it to a constant temperature. Interesting. Okay. Okay. So deactivated. Well, the convection heat transfer coefficient continues at X equals L, right? So this wall is hot, this gas is cold, this convection heat transfer continues, and this guy cools down, and that heat gets transferred by conduction through the wall and then into the gas by convection. Okay, so we're asked to solve a couple things. So first is determine the volumetric energy generation rate, Q triple prime, associated with the initial condition at time less than 0. Okay, number 2 is calculate the heat flux at the boundary exposed to the convection process at T equals 0. So that's going to be represented by Q double prime, Q dot double prime of X at X equals L and at time equals 0. Okay, we can do that. And then calculate the amount of energy removed from the wall per unit area by the fluid stream as the wall cools from its initial to steady state condition. Yikes. Okay, well, we'll tackle that when that comes along. All right, so what do we do first? We're looking for volumetric energy generation rate. So let's see if we can figure that out. All right, so we're going to make our usual assumption about constant thermal conductivity independent of temperature. And I should probably say also independent of spatial location, right? Didn't say that here, but it's assumed to be a constant for both. I'm going to assume that I have uniform volumetric heating, just like before with the coil problem. I just want to make sure that I don't have some random hotspot because I've got an impurity. So we'll say that the volumetric heating is uniform all the way through. And then I've got one-dimensional heat transfer, right? So one-dimensional means in the x direction from this hot surface towards this cold surface. I do not have heat transfer in the z direction up and down, up and down, excuse me. And I do not have heat transfer into the page or out of the page. And so, because I've just got one direction of heat transfer, when I get to the heat diffusion equation, um, in Euclidean coordinates again, right? Not cylindrical coordinates. We're in Euclidean coordinates because we're talking about a slab wall here. The time derivative with respect to, or no, the temperature derivative with respect to y and with respect to z go away, right? So those two terms cancel. And I'm left with just the one-dimensional heat diffusion equation, right? So I've got T dt let me try again. D squared T dx squared. So second derivative of temperature is equal to 1 over alpha times dt dt. So the time derivative of temperature, and then minus q gen over k. That comes from just multiplying everything through, or dividing everything through by k. And then I get this term, and then I take it to the other side of the equation, right? And alpha, as you remember, has k in it. So that's where that comes from. Okay, so just like we've done before, anytime you have a differential equation, you need an appropriate set of initial conditions in order to solve the differential equation. So now we're going to go hunting for those initial conditions and spatial boundary conditions. So the initial condition is actually given in the problem statement. So t of x at the initial time is 573.15 Kelvin minus 1 times 10 to the fourth Kelvin per meter squared times x squared. Okay, so that's our initial condition for time. And then one spatial boundary condition is, yeah, remember, right? We have an insulated wall, right? Insulated wall. And so what that means is that the derivative of temperature with respect to x is going to be 0 at x equals 0, where that wall is. So that's one of our initial spatial boundary conditions. And then the other spatial boundary condition is that at x equals L, right, which is where the wall touches the gas, that's convective, right? And so we know what that equation is. Okay, so so we're looking for, let's see, let's go back. Q triple prime associated with the initial conditions. Okay, so find Q triple prime by inputting pre-existing temperature profile. Here is that temperature profile, which is given to us, into the governing heat transfer equation. Okay, so let me see, what did I do here? Inputting pre-existing temperature profile. Okay, so okay. So this is a little confusing, but essentially, right at time equals 0, this thing is like sitting in a steady state temperature profile. It's got some weird, profile through it, but that temperature profile is not changing all the way up till time equals 0. And then at time equals 0, if I remember right, we shut off the heat generation term and then the wall starts to cool down. And so I'm going to rewrite my diffusion equation for basically time in the past, right? Time less than 0. And because it was in steady state all the way up until when I shut off the QGen term, at least for this part of the problem, this term is 0. The time dependent term is 0, right? Okay, so that leaves me with, hey, Poisson's equation. Okay, so I've got the second derivative of t with respect to x is equal to just minus q triple prime over k. And I'm just going to start taking derivatives, right? I know the equation of that temperature profile. Here it is. So I'm going to take some derivatives. So the first derivative with respect to x is just minus 2 times 1 times 10 to the minus 4, 10 to the positive 4 Kelvin divided by meter squared times x, right? So you can see here Here's the equation. This is a constant, so that goes away. This negative sign is that negative sign. This 2 is this exponent that gets taken down as I'm doing the derivative. This is a constant, and then I've got x squared, so the derivative of x squared is just x, right? 2x. So that's where this comes from, and then I'm going to take another derivative, right? Because I need second derivative of t with respect to x. So here's me just doing that. Here is the equation that I'm taking the derivative of. It's just the constant times x, and so all that gets left is just the constant, right? So that part is good. Okay, so okay, I'm just writing it again here. So second derivative of t with respect to x is just this constant. Oh, right. Because I'm using this equation, right? So so it's just this constant. So that's this value that I know, and then that equals minus q gen triple prime over k, right, which is here. And I'm solving for q gen, right? So I have to multiply both sides by k, which is a known value. So here I am multiplying both sides by k, solving for q gen all by itself, and I get 1.8 times 10 to the 6 watts per cubic meter. And this, again, is a problem borrowed from the textbook, right? One of the problems in the back, which I didn't choose for homework, but I figured I'd give you guys an example. So check, because I got the same answer that the book got. Okay, so step number 5 is, let's see, what are we doing for step number 5? Let me go back. What are we doing? We did this one. So now we're doing this. Oh, calculating the heat flux at the boundary, right at time equals 0. Okay, okay, okay. So, okay, so here I'm going to use that, the boundary condition, right? That I've got convective heat transfer at x equals L, which is the wall. So the temperature at x equals L and the initial time minus whatever the long far out ambient temperature is just equal to my convective heat transfer per unit area. Okay, and I know this equation, right? So I'm gonna, here I am writing it out, and I need to plug in x equals L. So here I am now plugging in x equals L and at time equals 0. So this term is a constant. This term is a constant. Here's my x squared, which is now 0.1 meters, right? Because that's the spot that I'm at, the x value that I'm at in the slab. And when I crank through, I get 473.15 Kelvin. Okay, so that is the temperature, 473.15 Kelvin. That's the temperature at this spot at time equals 0, right? So right when this problem effectively starts, when the clock starts, that's the temperature at that spot, which I got from just literally plugging in the value for x at that spot. Okay, and now that I have the value for the temperature at that spot at time equals 0, I can plug it into my convective heat transfer equation, and I can get the heat flux at that boundary, right? So here I'm doing that. So here's 1,000 watts per meter squared Kelvin. So that's a given value for H. Here's my calculated temperature at the wall. Here's the temperature of the gas that's blowing past, 293.15 Kelvin. And so I calculate this, I get 1.8 times 10 to the 5th watts per meter squared. That's my convective heat transfer flux. And again, this agrees with what I got when I looked in the book. Interestingly, this is not the only way to do it, right? You could also use conductive heat transfer, right? So instead of finding the temperature at this spot and then figuring out how much heat is jumping from the wall into the gas, I could also look at this spot but figure out how much heat is getting conducted from the slab into that spot before it gets picked up by the gas and pulled away. And I should get the same answer, right? Those should be equivalent to each other. So here I am just saying that, look, yes, the Fourier's law at this spot is true. So the first derivative of temperature with respect to distance multiplied by minus k is going to give me that conductive heat transfer coefficient, which is the same as that conduction as a which is the same as the convection at that spot, right? Both relative to the area. Okay, so here's that first derivative of temperature with respect to x, which I calculated before when I was going through my derivative. So there it is. And now I just have to plug in my known k value, which is this. And I have to plug in this equation, which is dt dx for a given value of x, which is 0.1. Again, 0.1 is the location right at the wall, right at the edge of the wall between where the wall ends and the convective gas is flowing. And I do the math and I get 1.8 times 10 to the fifth watts per meter squared. This should be an equal sign right there. But they are equivalent to each other, right? As you would expect. Right. So that's good. Um, okay. Uh, what are we doing now? Oh, okay. This one is pretty interesting. So now we need to calculate, right? So if we go back, we're now on three, right? So we did one, we did two, now we're doing three. Calculate the amount of energy removed from the wall per unit area by the fluid stream as the wall cools from its initial steady state condition. Okay. So the way that I tackled this one is I said, okay, I am going to write or draw a control volume around the entire slab, right? It's basically, infinite up and down, right? But I'm doing this on a per unit area basis, so it doesn't really matter how big it is up and down. It just matters that it encompasses the entire slab. And I'm going to say, okay, I know the energy of the slab is some value, and I know that the slab is conducting some of that energy away. It's actually convecting some of that energy away. Um, right? So that's a lost term. And so I'm just going to apply the first law of thermodynamics to the closed system of this slab and use that to try to back out what this total energy removal is. So here I am doing that. So the change in energy of the wall from whatever the initial condition is to whatever the far time in the future condition is where it's at steady state is equal to Q in minus Q out plus W in minus W out. You should remember first law of thermodynamics for thermo. Um, there is no heat transfer into the slab, right? And especially after time equals zero, there's no generation term either. So Q in is zero. Q out is this convective term that's leaving, right? So I'm going to leave that alone. And then I'm not doing any work transfer. So work in and work out are both zero, right? And notice, this is a little bit weird. It took me a while to figure this out. Um, this is a total energy change of the wall. It's not a rate of energy transfer. It's the total energy change of the wall from an initial state to a final state, right? No dots, no derivatives. It's total energy. It's joules, total energy of the wall that gets removed as the wall cools down. So it took me a little bit to figure that out. So all I'm doing from this step to this step is I'm just saying, okay, look, I've got a control volume, but I'm going to do this on a per unit area basis. So everything is going to just be put on a per unit area basis. So that's what these double primes are, right? So change in energy per unit area of the wall is equal to the change in internal energy per unit area of the wall, right? You remember that from thermo, we have a solid. And so the change in energy of the solid is just equal to the change in internal energy of the solid. That's thermo. And then I know for a solid that U is just MC delta T. But I'm doing this on a per unit area basis. So I take the volume and I take the mass and I divide by the volume, and that gets me the density, right? So the density here is taking the place of the mass because I'm doing this on a per unit area basis, right? So rho times C. Remember before I said, okay, C, P is given, but it doesn't really matter whether it's CP or CV because for a solid, CP and CV equal to each other, just C. And then here's the change in temperature of the wall. Right? So this is now my energy term, energy per unit area term, and then that equals my heat term, again, per unit area, right? So that's just, this guy leaving, right? Okay. Now, okay, so here I am just rewriting this, right? So I'm just saying, okay, this rho c delta T of the wall is just rho c times um, the temperature of the wall at its final state at T temperature, no, 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 T time equals infinity. And then here's the temperature of the wall at time equals zero. And that's my delta T, right? That's my difference in temperature between initial and final. Um, this would be fine if the temperature of the wall were uniform in space, but it's not uniform in space, right? Remember, I have that weird equation, right? Wherever it is, here, right? This equation that tells me what the temperature profile is in the slab at all time before time equals zero. And so this is not strictly correct because this temperature actually changes with spatial location into the slab. So to actually write this in the correct way, I have to write this total energy as an integral, where I'm basically taking the integral from T equals 0 to T equals L of the given temperature profile at T equals infinity and the given temperature profile at T equals 0. And that integral is giving me the energy, if I multiply it by rho c, energy of the initial state and the final state. So that's what I'm doing in this line, right? I'm basically just now taking the integral from x equals 0 to x equals L. So from this spot to this spot of the temperature field at time equals infinity, and then subtracting from that the temperature field at time equals 0. Um, and if I do that integration, I'm going to end up with the actual energy that gets transferred out of the slab by convection, right? So that's this equivalence. Okay, so here I am actually doing it. Here's rho c. Here's the integral of x equals 0, x equals L. Here I am putting that equation in. So here's the equation for the temperature gradient in the slab with respect to x. And that all equals Q out. And then here I am just, I just copy this from the previous slide. And then here I am carrying out the interval or integral, right? So this term and this term combined together to give me minus 280, but it's now a constant. So it gets multiplied by x in taking the integral. And then this term is a constant, but it's multiplied by x squared. And so when I do the integration, I get x to the third, but then I need a 1/3 to come down to negate the 3 if I do the derivative. This is a positive sign because I had a negative sign here times a negative sign, so negative times negative is a positive. And then this integral still is happening between x equals 0 and x equals L, where L is 0.1 meters, right? The edge of the slab here, L. 0.1 meters. And that still, of course, is equal to the total amount of heat that I'm dissipating by convection. So, okay, so here I'm just plugging in numbers. So here's my density. Here is my specific heat. Those two values are given. Notice kilograms cancels kilograms. Joules and kelvins are preserved. Um, meters cubed. If I take those units and then I multiply them by the units that are inside the temperature gradient profile thing. Kelvin cancels Kelvin, and I've got a meter here, which cancels with one of the meters in my denominator here, and I end up with the units that I want, right? Which is joules per square meter, right? Energy per area, right? So the units work out, which is great. And then I'm just plugging in numbers, right? So plugging in numbers and carrying through the math and solving for Q out. So the good news is that this whole thing comes out negative, which is what you expect because this guy is also negative, and so those negatives cancel each other out, and I get 7.77 times 10 to the seventh, lots of sevens, lucky number, joules per meter squared is equal to my convective heat transfer per unit area out of the slab. So let me just point out, right? Because again, we had some convection, and convection is weird, right? Because you can like swap things around inadvertently. I have convection heat transfer leaving my system, and so the leaving the system is a heat flux out, and so this negative sign comes from my first law treatment of that thermal energy leaving the system. I don't think, yeah, okay. I didn't actually like at least in this stage have to solve for um, a convective value, but I did in the previous step, right? So here in the previous step, on purpose, the wall temperature is hotter than the ambient temperature. This term comes first, and the ambient temperature is second, right? To make sure that this term is positive, at least in this calculation, and it should be positive here as well. And then it gets negated. It turns into a negative sign when I account for its directionality in solving the first law of thermodynamics. So I know that that's tripped people up, right? Convection is a weird bird, but the negative sign comes from the treatment in the first law of thermodynamics, not from putting a cold temperature first and a hot temperature second in that convection equation. Okay. Um, this checks with what the book says. So we're good. And hey, that brings us to the end. So three examples, a little bit of a lecture on conduction, heat diffusion equation, and boundary conditions. Thank you for sticking around this whole time. I know these lectures are really long. I sincerely hope that you're playing them on 2 times speed, so you only have to listen to me for an hour instead of two. But that's the end. And I will see you in the next one. Thank you for sticking around. Oop, now I gotta figure out how to stop my video given that my mouse is broken. There we go. Okay.